Yeah.
Hide all the windows.
Yes, yes, exactly. Hide the video.
There are two things.
Controls. Exactly.
Exactly.
Thank you. Ah,
Why are these solar power? There's a giant face limit and they're in a version of lamps. Why are solar power?
I don't know.
Like side of the tower, whenever we get an earthquake, all the pumps that we're using.
You don't have a power right temperature fluctuation. These No, actually, there's a little like gaseous cylinder where the temperature changes, it expands and contracts. It's with the rapid.
looks good. Yes, thank you, thank you. So that was the highlight, you know. Let's continue where we stopped last time. So let me briefly remind you, we had this query. It was an acyclic query here at the very top. And then we wanted to look at taking deltas to this query. And for instance, if we take a delta R, so instead of this relation R, we factor R, we just have its delta, then the delta of the query would be essentially commuting with this summation, right? You apply it here internally, and then because it's only delta R we have, the other ones, we don't have a delta for them, they are 0, then we only get delta R here. But then this delta R can commute with the sum because the R does not talk about these variables D and E, so we can push essentially these aggregates inside, and nevertheless, we'll still get, in fact, linear update time. Here is modulo log n in case we actually do it with sorting. Why? Because first of all, we have actually, so let's say we pre-compute this, so we have AC here and AC there, right? We still have to do for a particular A and B, joining with all the C's that are paired with that A, yeah? So it is still expensive. And what I promised you last time was that we can in fact get this to constant update time. And I remind you here by constant, we really mean here that is actually, you may still take time proportional to the number of variables or the number of factors in the query, but is independent of the size of the database. And that is important here, okay? So the question is, how can we achieve that? So we want to achieve this essentially using additional storage, which is the promise I made you last time, and that leads to so-called higher order IVM. And I'll explain in a second what means this higher order. But first, let's see how using a view can, in fact, materialized view can, in fact, lower the update time in that case. So assume for the time being this simple query, and then we come to the other, I think. So imagine we have these two guys, R and S, because it's a very, very simple query. In the previous session, we had it actually with the linear update time. And indeed, if you remember, the problem was that whenever we do update to S, right, we then to do a lookup here, and for that B value, we may have very many A values to pair with, and that would have to propagate in the answer. So that was the actual issue. But imagine the following situation, right? So this is the explanation. Imagine that now I use the following views. I say in R, I want to keep all the B's that I have in R, and I want to maintain the B's, the list of B's in R, right? At the same time, I want to maintain the list of B's that are in both R and S, let's say, yeah? Okay, so this is basically maintaining the B's would be here, right? We just aggregate away A, and maintaining the common B's is here. It's like an intersection, right, of the list of B's in this view. We just computed and in S, okay? And that we keep in this view where, I put conveniently as indices RS because it's about, information for B I get from both R and S, whereas here is only from R, right, to guide you a little bit with the notation. So if we do it like this, I can show you that we can achieve now constant single update time, single tuple update time. And the enumeration delay remains also constant, which is also a very interesting thing, okay? How can we get that? So I take these views I computed for you and I organize them in a tree. right? It's very convenient to organize it in a tree. Essentially, we have this factor R. I told you we compute a view on top of R that just aggregates away A, right? And then I have S, and then I told you that I could want to take the intersection on the B's from both this one. So I put this on top. And then at the end, let's say I even want to aggregate away B, right? So, but this is not that necessary. But imagine we also have it, right? So that's what we call a view tree. It's a tree of views. Yes.
So is VRS prime just a number?
So V prime RS here, what to do is effectively a nullary factor. So it maps the empty tuple to some multiplicity, right? So you aggregate away essentially the B you have here. Whereas here you have a single variable, a single column. Here you have essentially just the empty tuple. Yeah. Okay. And these are the views again, right? To compute them initially, it will take you linear time. Yeah. Under our assumptions. Yeah. And then we will see how we can update them and enumerate from them. So let's actually consider for updates, initially we want to update R. Yeah. So let's say this is our update for a specific tuple A0, B0. So we started the leaf. So we always propagate this update bottom up. Yeah. We started the leaf representing a factor and we propagate it all the way up. So we are here. Then this view, what this view says is basically discard B0, A0, just keep B0, okay? This is what it says. So effectively, this delta for the view we have here, right, maps this tuple B0, right, to the multiplicity of our original update. This is what it does. So this sum essentially here is, is pointless because we have a single tuple. If we have several tuples, then of course we have to sum up over all of them, right? So if you have a batch of updates, let's say, yeah. And what do I do now? Now I want to propagate this further, So what do? I have for this B0 to do a lookup in S to find out whether S also has B0. If it doesn't have B0, I will stop here. Yeah. If it has B0, then I will fetch its multiplicity, and I will have B0 here with that updated multiplicity. Yeah. So I compute in fact this delta for my view here. Yeah, with B0, and at the end I can also basically take away B0 and map the empty tuple to the multiplicity of that previous tuple from here. Yeah. So these are the deltas we compute now for the views. You see, I mean, we have to pay a price for using the views. We have to maintain the views as well. Yeah. But what is interesting here, if you look, is that at least for this specific case, everything we need to do would be just lookups, which if we assume constant time, then overall the time it takes is proportional to the size of this view tree, but that is independent of the size of the database, right? So that's actually the kind of neat trick, at least for the update to R. Yes?
So just to make sure there's a missing delta in front of delta VRS.
Yes, so here is a delta VRS, that's true. I will correct it after. Very good. So let's see now updates to S. So this takes a constant time, right? Updates to S now would be like that. We have delta S B0 here. Now we do the lookup on the other side. Yeah. And it's the same deal, right? It will be just one lookup and then we propagate up. Yeah. So this one will also give us an update time of O of 1. Yeah. Now, what do we do with all these deltas? Hold on. All these deltas now have to be obviously applied to the relations themselves, to the factors and views themselves. So after we compute the deltas, before we go to, let's say, another update, we take S, right? And we add to it delta S. Yeah. S plus delta S becomes the new S. R plus delta R becomes the new R, and so on and so forth, right? After every single update, we have to do this. Yeah. I mean, basically update the factors in the views as we go along, right? Okay, so that is also very important to do. Okay, so now, of course, you might think, okay, but this, you showed us a very simple example. Can we generalize this? Yeah, this is one thing. And the answer is yes. And I hope I get there. This is a special class of queries that admit this, which is, if you heard of acyclic queries, is that, yeah, has been mentioned. For alpha acyclic queries, there is a strict subclass called hierarchical queries, and they turn out to have this very nice property. But what is interesting about hierarchical queries is that they have this, they behave very well in a lot of settings. For instance, they are the ones for which we can do probabilistic inference in probabilistic databases tractably. I mean, in polynomial time, you know, in massively parallel communication model, if you want to do distributed computation, they can also do very well. I mean, Dan did some work on that, and I think you can do them optimally in one round of computation, if I'm not mistaken. And then, you know, in provenance, if you want to, for instance, manage provenance, right? That is, you know, the lineage sometimes is called, right, of the query results. It turns out that these hierarchical queries are those for which the provenance can be compacted or factorized in such a way that every tuple from the input is used only once in the provenance of any answer, right? So because of that, you can do a lot of interesting things with it. It's also the most compressed representation you can have. But there are, you know, in the finite cursor model, these are the queries that can be evaluated, for instance, in one pass over the stream, so you don't have to look back. And there are so many cases where they actually behave very, very well. Yeah. So this is not perhaps accidental that they turned out to behave also well in this setting. And I'll give you a definition of that, but a bit later. Yes. Yes.
So I see how we can maintain the views in update timing. Are you going to show us how we can now maintain Q in constant time? Sorry, I said in update time, in constant time.
Yes.
Okay.
I mean, yes. So effectively, I maintain these views in constant time. And now you will ask me, okay, what about the result? Yeah. So for the result, I'm going to show you how you can actually enumerate the tuples with constant delay, because the result may be very large, right? If you would, for instance, imagine you would do an update here, and we discussed this situation, right? And you would just like immediately, eagerly to get the final result, then and you look at the size of the result can be very large, right? But what happens with this view tree is that it keeps around all the information you need to recover fully the final result. But to recover the result, you only need to enumerate, essentially. So it's like, you know, you have an interface to this view tree that now accepts also the call enumerate or next tuple. It is as if below you don't know as a programmer, is it actually a list of records? Is it represented in a different way, like this factorized way? You don't know. Yeah. Okay. But you are guaranteed to get basically time proportional to the size of the tuple for every single record. Yeah. Which is in our case considered constant. So how can we enumerate? It's easy. But first of all, let me draw the following connection to the Yanakakis algorithm that you learned in the previous week, right? So what happens here is that you see, because we propagate this information always bottom up, then the information about the B here is always calibrated with respect to what is below. That is, these B's are guaranteed to be paired with at least one A. Okay? Because otherwise the B would not be there. This B is guaranteed to be also in R and also in S. Otherwise would not be there. You see? So this is the bottom up, right? Essentially calibration, the semi-join pass bottom up from Yanakakis algorithm. But we don't need also the top down one, because the enumeration does it for us on the fly, you know, if you want to enumerate the answers, right? So hey, closing that connection, right, that it should be easy now to understand that if we go top down, we can always are guaranteed, you know, in constant time to find the next answer. So imagine that first we are at the top, and now we ask, is this view empty? What does it mean empty? In this case, well, it maps, well, basically it has no empty tuple mapped to some non-zero, scalar. So in that case, we say, well, this means that the result is empty at the moment, so we stop. Yeah. But if it is not empty, we now can go to this view and iterate over the B's in the view. We assume this view is organized in a way that gives us constant access time, you know, using an iterator interface, like give me the next. I mean, you know, think of it as like in this particular case, it could be a hash map, right? and then we can iterate over it. It could be also just a simple list, a linked list, and so on, right? And we know that the Bs we have here will be distinct, right? If there is a B that appears many times, then the multiplicity will be larger. Yeah. So now, going from this, what we need for every B, we just have to basically go to R. Yeah. We could also here, but it's a useless step. We could go to R. Yeah. And we can fetch for every B the A's. Yeah. That requires, of course, to have an index that given a B, I can get a list of the A's. Right? So we need an index on this R. We could, in fact, organize R as an index from B to A to keep things simple for us. From the very beginning, we can cluster index like this, right? So if we do this, then the interface to R can say, for a given B, give me the next A, then give me the next A. We'll always get A's until the end when we don't have A's anymore for that particular B. And then we can close that and we backtrack and we go to the next B and we do the same. And because we are guaranteed that these B's are calibrated with respect to R and S, we know for sure that these B's will actually will have at least one A partner in there. Yes.
Okay, so I think I understand this, but I also don't understand why this is necessary. But like I'm sure there's a good reason. So if you go back to like the original query, which is Q of AB equals R of AB and join F of B, right? Isn't it kind of like already clear at this point that if we have an index, like we get like some update to S, right, which is a delta on our B's that are already unique, right? Like an update to S is like this B has like multiplicity, whatever, right? Isn't it kind of like straightforward that if we had an index from B to A on R, we could do this update in constant enumeration time already?
Okay, so let's actually break this down into pieces. First of all, imagine that you have here B's that are not there, and you are asked for an answer.
Yes.
So can you guarantee constant delay? No, because you may go over very many B's until you find a matching B.
Well, I have an index from B to A. Isn't that index
from B to A? Yes, but what about the B's from here with B's from there? You need somehow, if you want to enumerate them, right? You need somehow to be guaranteed, if you want constant delay, that if you do a lookup here, that lookup will give you something in the answer. You cannot just afford to look for, let's say, 1,000,000 B's until you find a B that actually is paired with the A.
I guess I'm looking at like the delta update query. So I have like, in the second line, I have like delta SB of 0.
Yes.
Can't I enumerate over all of the, like everything in my delta in constant time?
Yeah, so so you are saying that what happens if, for every delta I eagerly enumerate?
Yes.
Yes?
And then I
Yes.
look up the index and I apply that to
Yes,
my
yes. So imagine this situation, and imagine this. Okay, so it may be that you look up and there is nothing there and you do nothing. What happens if there is and you have linearly many A's? And then you say, okay, fine, it's perfectly fine. I can enumerate over them and I can output them.
Yes.
But then, there is, let's say, I want to delete that B0.
Yes.
Yeah, next time. And then you have to do again this effort, right? Okay. So in overall cost, if you think about it, you'll have to do a lot of operations there, which may not be necessary in the other approach. Because in the other approach, I only, when I propagate the deltas, I only keep the B's, I keep information about the B's. I don't eagerly go about inserting linearly many records in the output, only the next step to delete linearly many tuples from the output, okay? So that is the thing, especially in a situation where you don't eagerly want to, every time output the result after every single delta, because in most cases you might not want that, right? You might want to do a bulk of updates, and after that, at some point, there is an access request.
Okay.
Yeah.
So the view, I can think of the view as almost like a buffer that helps me
Exactly.
not do this so often.
Exactly.
Okay.
Exactly. Okay. And there is also the aspect of the buffer that somehow being more succinct, smaller somehow, and only focusing on the B's, it avoids this sort of pathological case where you have a heavy hitter that you insert, delete, and creates a lot of traffic. Yeah. And in between, you don't need this, access request, let's say. Yeah. Yes.
So is it fair to say that you want like an amortized guarantee on the runtime across like a sequence of operations?
Yes, exactly. And this is what we give here, right? So in order to capture this idea that we don't want to we would like to avoid this sort of pathological cases, we had to go to this more refined analysis where we had to split the overall computation time into time to do the update itself and time to actually access a record in the output. Yeah. Yes.
Yeah, it's not actually an amortization. There was no accounting for this. It's just a separation of two.
Yes. We will see later that it comes, this actually, in a more complicated example, will require some form of amortization. But for the time being, Joe is right. Yes. Yeah.
I'm just curious, like this tree that you're saying that you construct it this way in order to get optimality, right? For some more complicated like query that might include like more variables or something. Like, is there like an efficient way to do this, or is this just? Very good question. So the question is, what happens for other queries? I gave you a simple query. So the thing is this, and this is the kind of neat story here, that if you only look at hierarchical queries, there is a very simple way to construct it. Yeah, it's always possible to construct it. So it's basically in the nature of the query. And I will come and I will explain that. The idea with these hierarchical queries is that you have variables dominating other variables. What does it mean? A variable dominates other variables when the first variable appears in all the factors of the other variable, right? So it appears everywhere, it may appear also in other factors. So then you can actually construct it such that, I will come back, you construct a so-called variable order where the dominating variable is on top of the dominated variables. And from this variable order, you can then map to the view tree. So I will show you examples of that and I will work through examples with this. So variable domination is some sort of like partial order of variables.
Exactly. It's the partial order of the variables that allows me to factorize the representation of the query like this. You see, here the idea is also, in order to ensure this constant delay, I had to somehow break down the representation of the query result over several views. I don't keep it only in one view that I have to maintain eagerly all the time, right? I break it down into B and then the A's, yeah? And if you imagine more variables, then, these free variables or group by variables may be spread over very many views. And then, I start from the top, I get the value for the first variable, and then I look up in other views and I get variable values for another variable and so on and so forth until I construct a tuple, yeah? So this is also a very important aspect. If you want to maintain this sort of nice, analysis. I mean, nice performance in terms of delay and update time. Yes.
I know we haven't defined these yet, but are there async queries that are not hierarchical?
Yes, definitely. Definitely. And I hope I get there today to show you one example, but it's on the slides, in which case we cannot get this constant update time, but the best we can hope for, which turns out to be optimal, would be essentially a square root of n, the update time. And that is, according to the OMV conjecture, the best we can hope for. Okay, so I showed you this. And now the question is, okay, how can we generalize this example? Yeah. So basically, we have to construct these view trees, which was the point raised by Grace. But this is very similar to query plans for static query evaluation. In general, for acyclic queries, it's a bit harder, but if you take general conjunctive queries, it's even, it's like you want to find a good query plan, right? There has been a lot of work also in the database theory side on that, how to find that, which is an issue of cardinality estimation of the intermediate results, right? And how can we do that? You learn next week about the AGM bound, yeah, this fractional edge cover number, and then and this is actually a neat result, but this is still, in terms of practicality, far off. Yeah, it gives you some very loose upper bound, but because it only looks at the cardinalities of the relations and assumes the worst case scenario that can happen, which is of course not realistic. But then there has been, very much progress in the meantime, taking into consideration functional dependencies or degree constraints, like we know that the value appears in a certain number of tuples at most, right? And that can bound a bit this. And, I want to shamelessly advertise a bit the work I do with Dan, right? Which is on LP norms. So we can now be even more refined and look at the degree sequences in the data and look at the various LP norms on the degree sequences of our joint variables. And then we can exploit this to get even better upper bounds. I mean, that are closer to reality, to the real cardinality. And they actually in practice also turn out to be much, much better, actually. Yeah. So there is a whole subject here, which, is, I'm helpless. I will not be able to cover it in the lecture today, how to get basically a good query plan. Yeah. But the goal here is to minimize the propagation time for each update. So whenever you hit a view, how much it costs you is essentially the question. And there are two main approaches that I particularly am familiar with and I'm aware of. One is the DB Toaster approach of Christoph Koch from EPFL. And one is FIVM, which is factorized IVM from us, which actually builds on the back end of DB Toaster. It just does better view trees, essentially. Yeah. Now, in interest of time, I won't be able to show you examples with DB Toaster, so I can get to other things. But I will be able to show you examples with FIVM, okay, where the idea is that for all updates, similarly to the previous example you've seen, we use a single view tree. In contrast, DB Toaster will use different view trees for different updates, and then the number of views may increase a lot. And this actually jeopardizes even asymptotically the complexity, it turns out. Yeah. But the structure of the view tree will follow such a partial order on the variables as Grace pointed out. Yeah. So it is just a one-to-one mapping afterwards. And the query result will possibly be distributed over several views, as I mentioned before, in order to establish this, to acquire this nice result on the enumeration delay. Whereas in case of DB Toaster, to give you very briefly the idea, query result is just in one place, in one view. So it triggers an eagerly updating, deleting from there, and may be very expensive. And as I said, it may have several views. So let me actually show you. So these are extra slides for the DB Toaster example, and I will go over this. But I'm very happy to take questions if you have any later, by email or so. Let me actually show you, say a few words about FIVM. So when we want to construct a partial order on the query variables, yeah, we have to consider possible dependencies between the variables, the values of these variables. So let's say if the variables are in a relation, then in general you cannot say anything about that relation. Whether the values a variable can take are independent of the values other variable can take in the same relation. You may know about functional dependencies, and that can help a lot. Yeah. But in general, you don't know that. Yeah. So, we can refine this also under functional dependencies. But that's the thing. So this is why in my case, I intuitively want to have all the variables of a factor of a relation along the same path, essentially, right? To express there is no independence. Independence would be if they would branch out. Let's say I have a factor AB and a factor AC, they join on A, B and C do not need to be on the same path. And in fact, by having them branching out like this, what I'm saying is that given A, B and C are independent of each other. Right? So for a given A, the values I can get for B would be independent of the values I can get for C, because they come from different factors, from different relations. Yeah. So now a challenge is, can we find the variable orders that guarantee asymptotically, let's say, a minimal representation of such a factorization or the update time? And the answer is yes. If we look at the possible variable orders, we have a result that gives us this sort of optimality. Yeah, asymptotically, of course, not necessarily in practice. Yeah, but in the FAQ lecture in a couple of weeks, you will get back to the problem of variable orders, and you'll see there how you can actually get a good variable order. Yeah. So what do we do? So we look at the variable order we have, and I will show you in a second an example. And each variable will induce some extra views in our view tree. And the views, what will be there for, they will basically be there to join child views if there is a branching in the variable order, or they will marginalize out some variables, right, according to the order of the variables in the variable order. And we will put the input factors at the leaves. And that's the way we build the view tree. So let's see an example. So consider this query. Yeah, this is a cyclic. Yeah, and I decide for the following variable order. I realize that A dominates everything else because A appears in all factors. So I can put A at the beginning. In a sense, it's intuitive because if you fix a value for A, now you break down the query into little pieces, which can be done independently, right? So that's the intuition. So essentially what it means that given A, the values for B are independent of the values for CE and independent of the values for CD. Now, given A and C, the values for E are independent of the values of D. Yeah. So that I want this sort of conditional independence to be expressed in a partial order form. And this is what I do. I say I put A at the top because that's the root, because it's actually dominating everything else. Then on one side I have B, which is then on a different branch from the others, to express that is independent from the others given A. Now I put C on top of D on E because C dominates both D and E. Yeah. So that's the way you would actually approach this. And now let's see how we can construct a view tree from it. So this is the variable order I just showed you before. This is the view tree, and then we will look at it step by step. First of all, at the end of AB, we'll put a factor R, which basically, talks about A's and B's. At ACD, we put a factor S, which talks about these variables. And at ACE, we put a factor T, which talks about these variables, right? So these are the factors we have in there. Now, as you can see, somehow this view tree follows the structure of this. There are the same branches we have there, yeah? So effectively, we need, whenever we have here C, we need to have whatever comes below here to be joined, yeah? And similarly, here at A, we have to join them. And in between, I put some views that actually materialize, that aggregate away or marginalize out, the other variables that are not needed anymore. And why I do this? Do I do this? Imagine I wouldn't put this this view here that aggregates away B. Then we are in this previous situation where an update that gets propagated all the way here, we have an A, and then we do the lookup here, we may fetch a lot of B's. But that may actually mean that for that update, we get a lot of other subsequent updates further on. But if we aggregate away B and we only stay with A, then we just need a single lookup to get the corresponding A if there is any there, right? Okay, so let's first go over this and then I'll take the question. So we actually put these views, right, to basically at every branching point to join whatever is below, yeah? Which is essentially, it does always an intersection. They do intersections. And then I put the other views to aggregate away variables that are not further needed for joins. You see here, I don't really care about the actual free variables at the top, because I assume that they will be distributed over these views, and I should be able to somehow, by doing enumeration and look up over several views, to get the actual tuples, yeah, with a good delay. Okay, and now I can take your question.
So I think I should understand the view tree as sort of like a data structure that helps me lazily enumerate views so that when I have multiple updates that happen, I can be lazy and not have to do all of them eagerly. Exactly.
So it's somewhere between lazy and eager. Lazy would be whenever I get an update, I only update these guys, the leaves, right? The factors. Eager would mean whenever I get something, I compute the delta and I propagate all the way to the top. This is like in between. It's like I actually want to have the complexity of lazy for the updates, but I want to still do a little bit of work. So I want to piggyback in the update some work that will help me later at the enumeration time to be fast enough.
Asymptotically, it's still constant work.
Yes, exactly. And that is the issue. If I can still do it within the same time budget, if you want, right, of the update, then I win. And I don't show you here experiments, but we have papers comparing these sort of approaches with other approaches where the gap in performance can be orders of magnitude actually, right? While also not using too much space. Yes.
I'm just trying to think of another intuition for this. I don't know if this makes sense, but is it one way to look at it? You're sort of like trying to arrange these things. Imagine you're looking at them as tensors in such a way that as you go up, you're always performing some sort of like a contraction or a projection or something. So you're always sort of losing data or like making your tensor smaller as you go up.
Yes.
So that you never have to go sort of like expand your tensor.
Yes, exactly. So this is a very good observation. First of all, what you see in these intermediate results is that their variables are always included in the sum set of variables at the leaves. Yeah. So they never, for instance, have to combine variables from different factors because that will be a blow up. And that would be against all your idea, essentially, right? So you always contract, but when you join on common things, right? On common variables, right? So that is a very important point. And yes, as you notice, whenever you actually join, effectively it is like an intersection. Yeah. Okay. Yes. Yeah.
I'm curious if like the parallels with like probabilistic inference came first, or if this is like something that you realized after this theory was developed.
So probabilistic databases came first, 2004, a VLDB paper, highly cited, yeah, that introduced hierarchical queries, yeah. Then people started realizing in the finite cursor model that we can do one streaming, one pass over streams evaluation, yeah. And then I came up with this provenance, and I realized, if I look at the lineage or provenance of these queries, I can represent them in so-called read-once formulas, where every variable appears once. And that would explain why they are also tractable in probabilistic databases, in fact, because if you have such a formula where the variables are random variables, it's easy to compute the probabilities because the variables are independent. You do disjunction of variables, conjunction of variables, right? And then Dan worked on a massively parallel communication model, looked and realized that hierarchical queries are also very interesting there, right? And now it turns out in 2017 there was the realization in the context of this IVM, yeah. And actually yesterday we made another realization that connects it to intersection join queries, where you want to join on intersection on intervals. You have queries on intervals. It turns out that this corresponds effectively to the class of such queries that actually admit linear time evaluation, modulus and polylog factors, and everything else needs much more time, right? So what I'm trying to say is that there is something about this class that makes it very, very amenable to a lot of type of processing. And the relational AI, we implemented this stuff with these hierarchical queries, and in fact, we try to push it further. How can you push it further? One way is to say, what happens if we have functional dependencies? Then suddenly a lot of queries become hierarchical, yeah? For instance, in TPCH, if you just look at the joins, about 20 queries, about 20 out of 26 become hierarchical because of the key foreign key joins, right? And this is a neat property. And then we said, okay, what happens if we actually assume that some relations are static, right? That is, you never update them. Then suddenly you can ensure the same nice complexity for more queries. What happens if you have queries which are not hierarchical, but you also have to maintain at the same time a bulk of other queries which are hierarchical? It turns out you can use them to actually do efficient maintenance for the non-hierarchical queries. And there is much more that we do in this space, but all motivated by the fact that we want to see how far we can go with this very good complexity, yeah, which actually, is one of the good cases where database theory can also show some practical applications, right? That where indeed it makes a very big difference in practice, because the algorithm is not complicated, you see, it's still very, very simple. And you can very easily get the variable orders, you can very easily get the view trees, and so on. Yeah. Yes.
So, I mean, there's this connection to graphical model inference, right? There's this
Yeah.
baseball algorithm that feels very, very similar to this. I don't know if that was the nature of the question, but that was what I was wondering as well. It's like, what's the chicken and egg with conditional independence and graphical models in this work?
So, okay, so you can have trees there, right? And we know that we can do well on trees for graphical models. There are nevertheless several differences. These trees, I don't think they actually correspond exactly to hierarchical queries. They might correspond to a superset of them, possibly, because they represent acyclic ones. Yeah, this is one thing. Another thing is that they typically look at the dense domain. And then the situation is totally different there. Whereas here we are in a sparse domain. And in addition, what we have here is that we can insert and delete, well, we can insert at least tuples that are not yet in the database. In the graphical model, think about it, right? The domain is somehow fixed. What you can do in terms of updates, you can come up with some belief that will actually change some probabilities associated with pre-existing tuples, right?
Changing multiplicities, if you will.
Yeah, exactly. So, and it turns out that in some analysis I've done, just limiting yourself to a predefined domain can make things much, much simpler. So you can get much more, we can get better results. right? But the database setting is a more general setting because of the sparsity and because of this possibility of inserting new tuples, right? Which are not there. Also, this makes it different from, let's say, things like matrix multiplication and so on, where you know for sure what is the dimension from 1 to n, 1 to n. All you do is change the values in the tensor, right? Whereas for databases, it is as if suddenly you add another column or you add another cell somewhere, you know, and you know, yeah. So it is a more general and therefore a bit more complicated setting what we have. Yes.
I also want to add, so because there was this question about graphical models. So graphical models indeed are tractable if they are acyclic. But the big difference is that an acyclic query does not give rise to an acyclic graphical model. The query is just a high-level representation. You need to ground it. And once you ground it with all the data in the database, if we see a Boolean formula, I think we did see Boolean formulas as a result from grounding a query.
What grounding a query?
It means substituting the variables with constant from the database, and then the query expression, which was the first order sentence, becomes a Boolean expression, a very large Boolean expression. And you started with a simple query that was like a chain of length 3, and what you end up is a huge, complicated Boolean expression that represents all possible paths of length 3 in the database. So this is where the discrepancy ends. An acyclic query is not by far a simple graphical model. It's a difficult graphical model. A hierarchical query, which is much more restricted, turns out to be a simple graphical model. But even there is a wrinkle. You see the distinction.
So the query would be like a first order specification, whether the grounding means, you know, is the propositional level, where you basically, you know, look against your facts and then you materialize all of them according to the pattern given by the first order sentence. Yeah. Okay, so let's see actually updates, but it will be completely unsurprising to you now because all I'm going to do would be just simple lookups. It is as if to update this, I don't even need joins, right? You know, it's just simple lookups and propagation up. Yeah, so I do a lookup, you know, I start here, then I basically marginalize, then I do a lookup in VC, right, to find out whether I have an A0 there. I propagate it further up, and that's VA. Okay, so then for each updated view, of course, I then after the update I do this operation. So I apply the updates to the view. Okay, so now let's say we do delta S. You know, I want just to convince you that it's the same thing. Simple, marginalization and lookup. Yeah. Okay. So that's exactly the same as you'd expect. And again, we just update and then everything will take a constant time. Yes.
When you update S like all the way up from S or just or
so I basically apply the delta here, and then I compute the delta here using this expression, which is delta V is just basically I take its payload, I just throw away E0. And then in order to compute the delta here, I do from this delta a lookup here. And I compute the delta here. Then I compute the delta here by just throwing away C0. Then I do a lookup here, and then I compute the delta here. And then I compute the delta at the top. And once I have all these deltas along that path, I will then apply them to the corresponding views. Right, so that I update the views. So next time when I do an update, I take into consideration whatever the update produced here. Yeah. Good. And then also to T. So for completion, because you have access to the slides, I put it there so you can see it as well. It's also a similar propagation, right? So now, if you want to enumerate, this is a little bit more complicated, perhaps because it has more variables. So we have a top-down enumeration. We start at the very top. And again, the observation is that this view has A's which are calibrated everywhere. So the A's that are here must be also in R, in T, and S. Because this is by nature of the propagation, right? We maintain them calibrated. Okay, this is very important. So therefore, and why is this important? Because we are guaranteed then when we look down, right, with an A, to get at least a matching tuple in any of the views below that have A, right? So then for every A, we are guaranteed in constant time to find the matching. So therefore we can ensure the enumeration delay remains constant. Otherwise, imagine we have here some A's which don't appear here. Then we may have to iterate over very many A's until we find one that matches there. And the number of these attempts may be very large. So then we cannot guarantee the delay to remain constant. Yeah. So that is an important bit. So we do it as you would expect. We look at VA, is it empty? If yes, we stop. Otherwise, we start iterating the A's at the view below. And for each A, what do? We look up into this. So we need this sort of index for each A to have access to the B's. And from this one, we look here. So for each A's, we have to we need access to the C's. Yeah. And basically what it happens here, and this is a question which I didn't get. I'm surprised I didn't get it. But what about multiplicities? Right? How can you get the proper multiplicities? Well, the multiplicities you get now from this, right? You don't use the multiplicities from these guys, right? Because this, of course, is an aggregation of the multiplicities from this. But if you want the true multiplicities, effectively, whenever you fetch the tuple here and there, you take their multiplicities, multiply them, you know, and that will be the multiplicity for A, B, C, yeah? In our case, because A, B, C are the free variables. If the free variables would be actually all of them, then you'll iterate from here, but you also have to iterate from here to get the D's, right? So you have here an index from A mapping to C. You also need from AC mapping to D and from AC mapping to E. And then you don't get multiplicities from here, but from here, here, and there. Yeah. Okay. So that's the way we do. We output then a tuple, and then we backtrack to the previous view in the structure. Good. So yet the kind of, you know, terrible news is that even with this nice thing, these approaches that use higher order IVM, that is, you know, they use views that are maintained themselves, and to maintain these views, you may need to maintain other views and so on and so forth, right? A cascading of views. They are not necessarily optimal in general. Yeah, and I will show you one case where they are not. And that's the rest of the session for today. I will show you for the triangle count query that the current approaches, you know, they produce something suboptimal. Then I will show you a simple lower bound for the triangle count query, and then we see how we can overcome that and get an algorithm for it. Okay, and here I have slides, extra slides for you in case you want to understand that, how we can do triangle count with these approaches. Okay.
Triangle count isn't hierarchical, right?
No, it's not hierarchical.
Is this optimal for hierarchical, for all hierarchical?
So that will be optimal for all hierarchical, but if you go beyond hierarchical, what do? Right? So that's the question. And now I show you a case that remains optimal, is not hierarchical, and its update time is not actually constant. Right? So that's the next thing.
That's a triangle query?
And that's the triangle count query. The triangle, so that is also for the triangle query, we obtain the same optimality, but I'm going to show you the triangle count because it's even harder somehow. For triangle join query, you think that, oh, somehow optimality, you might relate it to the number of tuples you have in the outputs, right? But for the triangle count, the output is just a constant. How can you possibly reason about optimality in that setting, right? Well, it turns out we can. So let's see. This is the triangle count, you know, A, B, B, C, C, A. Here is in a more general setting where R, S, and T may be just different factors, not necessarily the same edge relation. You know, this is a hypergraph representation of it, right? And we want to maintain it under single tuple updates to any of the underlying factors. And the question is there a fully dynamic algorithm that can maintain the exact triangle count in worst case optimal time? And the answer is yes, and let's see how we can do it. So first of all, let me show you the naive maintenance, which is recomputing from scratch. Imagine that these are the contents of the factors. That is the sum at the end. And we come with an update to R. We just, let's say, extend it a bit, you know, visually. So what do? We just have it. We just apply the change to R. We get the new R. We do again the query, right? And that's a valid way to do it. If n is the database size, the size of these factors, right? Then the update time will just cost you this, n to 1.5, which I mentioned also before, and that will be the subject of the lecture next week. But we'll see another way to achieve the same thing today by doing a stream of inserts, n inserts, each insert costing square root of n time. Overall, n times square root of n will give us n to 1.5. Yeah, and this has been subject to intensive research. You know, I took away a slide showing how much work has been on the triangle. You know, it is amazing. Like, you know, whenever theoreticians want to show something non-trivial, they take the triangle, because this is where it differs a lot from classical database systems that actually do not give you this complexity. They give you quadratic time, because they do join at a time, and then basically what they do is that they join two of the relations. They may get something in worst case quadratic, and they then use the third relation to filter. Yeah, but that remains still quadratic time. And you know, there are simple databases that for which you can show that it doesn't matter in which order you do the joins. It will still get, you'll still get a quadratic intermediate result. Yeah. Okay. You can do better than this for the count if you use Strassen-like matrix multiplication techniques. Yeah. But nevertheless, you will still get supralinear. And the space, the space you need is just linear, because you need to store the input factors, right? So now the first order incremental maintenance, what does it do? We compute the delta, right? So if we apply a delta here to R, this is the delta, the single tuple, then the query becomes simpler. Then you fix B to be beta here and C and A to be alpha here, the constants. So effectively what you need to do is intersection on these C lists, right? And then that intersection, because this may be in worst case linear size, yeah, will take you linear time. Still better than what we've seen before. You then patch the query with the new delta. So you still need only O of n to store the input factors, and the update time is O of n to intersect these lists. Yeah. Now, if you want to do higher order maintenance, imagine you want to compute the delta using the materialized views. So what do? We say, let me actually construct a view here. Yeah. This is the view that that marginalizes C, you know, BA, so that when I have an output, an update to R, I can quickly look up into this view, because the view is only over BA to give me the answer very quickly. Yeah, which is indeed what we can do. This becomes the view. Then the lookup here is just a lookup, you know, the tuple here becomes a lookup there. And then we actually can do this in constant time. Now, I put something under the rug, of course, which is how can we maintain this view? Yeah, you know, I mean, we have to maintain the view as well, right? Because otherwise we don't get the correct evaluation. So imagine I do an update to S, then the update to S might give me a C value here, gamma, which is actually, you know, will have very many A's in T. And that is actually the problem. The problem is that the number of these A's may be linear. And then if you do the same also, if you want to do update to T, it will be similar. So it will remain actually linear. So you don't really save much, except for the case where you know updates are only to R. Then you can save, but of course you need to pay some price for that, namely materialization of this view, which is actually quadratic time, which you can do initially. So if S and T are static and R is the only dynamic relation, that would still work. But in general, if you want updates to any relation, any factor, then that's not a good idea. Yes?
The average case update can't possibly be linear though, right? Because you run out of matches, right? If you pick random gammas.
Exactly. This is a very good observation. This is actually what we cook at the moment. And there is a special result, which we will have, hopefully, you know, in a couple of months, which shows the following. Now, I mean, we didn't write it down, but there is something called the query decomposition lemma that says that at least for inserts, yeah, you can do this. You can actually consider, you iterate over these tuples that you may insert, you do the lookups in the other. Some lookups may cost you more, some others will cost you less, inherently less. For inserts, you are right. We can maintain this on average constant time. However, what happens if you have inserts and deletes? And this is what we are going to show, that inserts, if you allow both inserts and deletes, then the problem becomes harder than just inserts alone. And why is this? Imagine I do insert and I hit that very, very heavy C, right? And I have linearly many guys, but then I do a delete exactly with that C, and insert with that C, and delete with that C, right? So basically, you know, I hit that worst case scenario all the time. And that makes it harder. So if you have only inserts or only deletes, the problem turns out to be easier. If you have both inserts and deletes, you better watch out. You have to do something about these heavy hitters, which is exactly at the core of the solution to solve and not get linear update time. Yes.
So it's like drawing with replacement versus without replacement.
Sorry?
It's basically drawing without replacement versus with replacement.
Exactly. Yeah, exactly. So you can phrase it like that. Exactly. Yes. Yeah, so let me show you a very simple proof for the lower bound, right? Because it's a database theory class. Yeah, and so this is a Boolean triangle query, detection query, which is a much simpler version of the count. Essentially, this one tells you 0 or 1 instead of telling you the number of triangles. And we'll show that already this version is hard. Yeah, hard in a certain way. So what we can show is this, that if we have a database D, yeah, representing our factors, and n is the number of tuples in the database, then for any strictly positive gamma, there is no algorithm that incrementally maintains this query with this update time and this enumeration delay. If you would be able to come up with such an algorithm that you will actually violate this conjecture called the online vector matrix vector multiplication, which turns out now, which, you know, it's quite interesting that exactly at this moment at Simons, there is a refined complexity analysis program which deals a lot with such problems. And in the talk we had by Monica Hensinger the other day, right, she showed basically this problem as being, this conjecture to be at the bottom of very many problems in graph algorithms, actually. The dynamic problems, exactly, yeah. And I will tell you what is this and what this means. This means that you cannot get below square root of n and below linear at the same time. Yeah. So what is this OUMV problem? This is this. You have a Boolean matrix M. It's a Boolean, 0 1s inside. Yeah. It's n by n. And you are given n pairs of vectors, u and v, right? Such that what you want to do is to compute this u transpose mv, which is a scalar. Yeah. But you see, the way you are given makes it a dynamic problem, because you are given a pair of vectors and you are forced to give the answer to this computation. And then you are given the next pair of vectors and you are forced to give the answer, and so on and so forth. So it forces you to propagate the update, kind of, you know, to compute it. Yeah. It doesn't allow you, for instance, to do tricks like, oh, what if I have all the u's together, all the vectors u or all the vectors v together? If I can have them all together, then I may do very many tricks that involves matrix multiplication using Strassen's algorithm, which will then will allow you to do computation much more efficiently. But no, we force it, yeah, so that you don't use Strassen. So that's the idea. So the OUMV conjecture is that there is no algorithm that solves this problem in subcubic time. Okay.
So that was Monica Hensinger.
So that was, I'm not sure, I don't think it is her, you know, conjecture, but she has a nice survey in Stock 2015 where she actually shows a whole lot of problems that are based basically on this conjecture, right? But I think the conjecture is dating a bit earlier by some other guys, some Japanese guys. I apologize, I forgot their name. But I'm citing here her paper because this is where she showed that a lot of problems actually depend on this conjecture, can be phrased, can be optimal, conditional on this conjecture. Good. So how can we do it? Usually with lower bound proofs, you proceed as follows. You have an oracle, right? So assume we have an algorithm that can maintain the triangle detection query, QB. And this is A. This is our oracle, yeah? And we say that we can maintain it indeed with this time, which is actually deemed not to be possible. And what we do now, we design an algorithm B that uses this oracle A to solve the OUMV problem, right? So this means that if we can solve the OUMV problem using the oracle here, it means that if possible, we can solve this problem in this time, then also the OUMV problem can be solved in that time, right? Okay, so this means that basically we violate the conjecture. Yeah. Okay. So that's the thing. And yeah, so we design an algorithm B that uses the oracle A to solve OUMV in subcubic time in M. Yeah. And this contradicts the conjecture. So this is the algorithm. It's very simple. We take the factor S, let's say, to encode the matrix M, the big matrix. How do we do it? We know at position ij, we put the matrix entry Mij. Then in each round of our problem, we do this. Factor R will encode the vector U, and factor T will encode the vector V. How do you encode it? Just straightforwardly. But because R is binary, is not unary just for the vector, we just pad it for the values of A just with a constant A. That doesn't somehow hinder, right, the multiplication. Yeah, so this is just a constant A. Similarly for the factor T, yeah, we encode the vector VR, but because we have is binary for the second column, which would have values for A, we just put a single constant A everywhere. Yeah. Then we will see as an example. Yes.
Should A be the round, kind of related or unique for each round?
M?
A, the constant A. I'm trying to see where is A coming from.
No, it's a constant. It doesn't matter.
It is the same constant for
it could be the same constant. It could be also a different constant. But it has to be just one. So that the join of R and T on this column does not hinder the other combinations. So it basically, so that the query becomes exactly, the answer of the query becomes exactly the result of this matrix vector multiplication. So then we check with our oracle that the answer is 1. And if the answer is 1, then basically our matrix multiplication becomes also 1. And I'll show you an example now. Yes.
Why do we need, like, doesn't this suggest that the query R of like I, S of ij, and T of j is also just as hard as
yes
this?
Yes, exactly. And that is a non-hierarchical query.
All right. Cool.
Yeah. So effectively, what you say is, what happens if we have just a query where we don't have this column here in T, and we don't have this column here in R? Yes, that would be the Rx, Sxy, Ty query, which is the smallest non-hierarchical query, which is also then hard, and as hard as the triangle count here. Okay, so let me show you an example. Imagine that this is the vector. I put it transposed, so it's a horizontal here, has a single one. This is the matrix, and this is another vector V. So you see, basically U and V represent indices into M, right? So if this is 1, position 2, we look at the row number 2. This is 1 at position 1. I look at the first column, and if I find here this cell of 1, then 1 and 1 and 1, they make a 1. And that is basically the result in that case. Yeah. But of course, I may have other ones, and I may have a 1 here as well, 1 there as well, and so on. And then I have several ones, but the Boolean says there should be at least a 1. Yeah. So one of the combinations should be valid. So how do we encode this in the factors? You see here in R, because we have this A, we don't want to use, we just put a constant A. And then the second position we encode here is like we do basically a tensor encoding of that, right? So we have the position 2 here for B, and the value is 1. Okay. Here in the matrix, we just write down all the combinations, but you see, we don't need to, we can write in a sparse way. We don't need to write those entries where it is 0, the value. So we only write 2 and 1, 3 and 1, 2 and 1 and 2, 2 and 2, and 3 and 3. These are the values with the 1. And similarly here, just the first entry, is 1. And now if you do the multiplication here and the counting, you get 1, which, is the one we want to have. Yeah.
Yeah. I think I'm lost here. So where does insertion or the incremental maintenance and the triangle play a role?
I will show you in a second. Okay. And this is basically done the next slide. Yes.
So kind of related, so the R and T are not the deltas, or they are the deltas?
RT?
The R and T are matrix.
No, so the moment I show you the encoding and how it corresponds from the matrix vector to the factors. And we'll see in a second updates, how updates can be processed.
Okay, so right now RC are all kind of static.
Yeah, static. And now we actually are going to solve the OMV problem by simulating inserts and deletes in the database and then solving the triangle count query. Okay?
We're just showing this is correctly mapping the two problems. So this corresponds to the bijection between the two problems. Yeah, I'm confused because like U and V are dynamic, and then R and T are not dynamic. So,
hold on.
Yeah.
Hold your horses. It comes exactly on this slide.
Yeah.
So what do we do? So we do as follows. at the very beginning, we are allowed to have some pre-processing time. So what we are going to do is this. We are going to do n square insertions into relation S, right? Okay, so we have this algorithm that actually does the maintenance for triangle count. And now I am OUMV and I say, okay, this is my M. You know, insert, you know, basically into S, you know, at most n square entries corresponding to my entries in the matrix. Yeah. And then what I do is next is I say this in each round, right, of my OUMV algorithm, I do this. I ask the oracle, hey, to delete all tuples in RNT. Yeah. So because RNT are just at most holding the vectors, so n distinct values, right? The distinct entries, this costs me at most 2 n deletions, because some entries may be 0 anyway, so I don't need to deal with them. Then I insert into RNT the new vectors in that round, okay, which costs me 2 n insertions at most. Yeah, you see, I have to do delete and I have to do insert. And then I check, and that is the enumeration phase, right? I check whether QB is 1. So I have to evaluate the query. My oracle evaluates the query. And this holds if and only if, basically this is actually 1. Yeah, the multiplication of the vectors with the matrices is 1. Yeah, because, you know, I already explained you before why, and I also gave you an example. Okay, so now what is clear is that B constructs a database of size O small n squared, right? Because, you know, we have this M like that and the others are just linear. Okay, so now let's do the analysis and see what happens. So our claim is that there is this such an algorithm that can meet this update time and this delay. What is this? Because this is the size of the database I just mentioned, it's n squared, small n squared. And I claim that I can do it with this time. And big N to the power of 1 over 2 minus gamma. So that was my claim, that I can do this. I can do this with my triangle count algorithm, maintenance algorithm. So this is the update time, and this was the big N to the power of n minus 1 minus gamma, right? So that's basically what I know I can actually do with my algorithm A that maintains the triangle count. Now let's see, for every single such operation, what would be the cost that my algorithm has to take. So the first cost is this. Because I have to do n square updates in worst case, each update costs me this time, yeah, which is exactly the one I have there. If you do the math, you get to something like cubic minus, you know, n to 3 minus 2 gamma, right? So that's the time to do at the beginning, right? This pre-processing. Now we go in each round. And in each round, we do this. Because we have to delete from both RNT and insert in both RNT is like 4 times n at worst, right? And for each such update, this is the time to do the update, which is the time over there, right? Which becomes something like that, n to the power of 2 minus 2 gamma. Okay, so that's the time per round to basically update the relations RNT. And now I have to do the check. To do the check, I have to get the delay, you know, to basically get the next answer, which is the only answer in this case, right? Which is this delay. Yeah. And I put it in there, and that's the delay. Okay, so that is per round. Now let's look for all the n rounds. What happens? For all n rounds, I have to multiply the quantity this and this plus this. I have to multiply it with n, and I get to something which is n to 3 minus 2 gamma. Why? This n times n to 2, yeah, and also n times n to 2 here. So it gets basically subcubic. Okay? Oops. But that is actually a problem. It contradicts the OMV conjecture, because it says that because my algorithm A can do it so well in this with this update time and this delay, yeah, then it will also be able to solve the OMV problem in subcubic time. But that contradicts the OMV conjecture, which means that no, I cannot really get it with that sort of good update time and that delay. This is what it says. Yes.
So isn't like step 1 not necessary? Like we don't like, because we could start M as the entire database and then get the views. Okay,
Yeah.
cool.
So the first step here, we can call it a pre-processing step because it's not dynamic in any way. You just do it at the very beginning. The matrix M remains the same, but the other ones are dynamic. because, you know, they have to proceed in sequence. Yes.
Are there algorithms that have gamma as a function of the database? Like where you have, so gamma is not a constant, but it's a function of the specific database, so there are algorithms like that.
So in this case, what it says is that it doesn't matter which gamma you come up with, as long as it is strictly positive, you contradict the conjecture.
But it's independent of n.
And it's independent of n, yes.
So I'm asking like, are there algorithms that are not where you have some, it's not a constant, it's a function of n or something like that?
So basically, for any gamma, it shouldn't work, regardless of the database.
No, but I think there are super smart algorithms where gamma is, I don't know, log, something like this.
But in this case, it cannot be, because it would contradict the conjecture, right?
It is a conjecture for a fixed constant gamma.
It's for any gamma.
Yeah, any number, not any function.
Gamma
No, any number.
He's asking whether gamma depends on the database.
No, it doesn't depend on the database. No.
Right.
Yeah. Okay, so that's basically the thing. And now I would like, in the remaining part, if you still allow me a bit, I would like to also close the gap, the complexity gap, and show you an algorithm that can do this. Yeah, let's see how far I can go. Yes.
Yeah, this might be a subtle point that's not very important, but like I think in the reduction itself also needs to be like in that time. Like in polytime reduction, we have to make sure we have a polytime reduction. So I think that's why the first part is actually necessary. So we need to show the encoding itself can be done. It's bounded by.
Yeah, but the encoding is also done in each round, right?
He's
Yeah.
responding to my question.
I see.
Yeah, in the beginning. So that's
Yes.
something that we're doing the encoding.
Yes.
You could also do in n to the 1.5 using that other algorithm, right? For n squared, because you have n squared insert and then n.
You see, the problem is you can allow here in the pre-processing time anytime you want.
Yeah.
Because at the end of the analysis of all the rounds, you are already subcubic. So even though here I may take, you know, whatever time you want, still I will contradict the conjecture because of this step here, because of the dynamic part. Yes.
So this conjecture, like one of the intuitions is that you can't use Strawson style optimization.
Exactly,
So
exactly.
you can't beat
Yeah,
n cubed. So there's a proven lower bound for monotone circuits that you can't beat n cubed for matrix multiplication. Is there a connection between these two formulations, the incremental vectors and the prevent, like not allowing negation?
I don't know about this, but it seems to me that if you force the OMV problem to proceed like this, step by step, the negation is of no use really. So that's my intuition at least. Yeah. But yes, it is made so strict so that it avoids tricks like that, using negation, using, you know, essentially over calculation and then compensation, which is a form of negation, right? Like you compute more, but from that more you can then easily take some differences, and then you get many entries in the many cells in the matrix. Yeah, exactly. So they are related, in fact. Yeah. So if you would not be allowed to use negation or difference, then the problem will become I mean, you will not be able to solve it as fast as, you know, with Strawson. Yeah, so Strawson is essentially based on that. Yeah, using these cancellations, if you want, you know, at some point, or overcompensation and then taking difference. Good. So this is the known upper bound. This is the known lower bound. Is there anything in between? Yeah, and it turns out there is. Yeah, and then we can do this in this amortized time square root of n. Yeah, and this is worst case optimal then, because it matches this particular one, right? Because for no gamma strictly greater than 0, we can have that. So the best we can hope for is to just match that. Yeah? So this is in fact the result. The result says that we can actually have a family of algorithms to do the maintenance that are parameterized by an epsilon, which is from 0 to 1. And then the amortized update time goes like this, right? It can go, when epsilon goes from 0 to 1, you can go from something linear to something which is square root of n, and then can grow up again. But then it has a trade-off with space, which actually, as the update time goes low, the space increases, and it can increase up to 3.5, n to, 1.5, n to 1.5, and then it decreases as well here. And, you know, some of the approaches we've seen before would represent, you know, some of the extremes in this space. right? And the optimal we reach here, of course, because this would be the lowest point we can have. Okay, and in fact, we showed later on that we can even do this linear space. So the space doesn't need to increase and decrease. Stays linearly while we also decrease the thing. But that argument is much more involved. So let me show you how we do this. We have to compute the deltas like in first order IVM. We have to materialize views like in higher order IVM. But the new ingredient now is that we have to use adaptive processing based on data skew. So that is, we have to treat the heavy values differently from the light values. So what is this heavy and light? Imagine I have this factor R here, yeah, and I partition it on A, yeah, in the following way. If this A has many B's, well, has less than n to epsilon B's, I put it in this part, which is index L, which means light. So all these A values in here are light, yeah. Whereas if another value A prime has more than n to epsilon, then I will put them in the heavy part. Okay, so then it's clearly that if I take the union of the two, the plus of the two, I get in fact the original relation, because the value can be either heavy or light. And I do this basically for all others, yeah, relations. I partition based on their first variable, and now we have actually some very neat bounds which we know. First of all, we know that if we look in the light partition, in the light factor of R, and we look at a particular value of A, how many tuples can we get? At most n to epsilon, because it's light, that A is light. But we also know at the same time that if we look at the heavy guys, how many possible heavy guys can we have? Think about it. If every heavy guy appears at least n to epsilon times, and the whole factor is of size n, we cannot have more than n to 1 minus epsilon heavy guys, right? This is also a very important constraint on the sizes that we are going to use in our analysis. Is this clear? Yes? Good. So we partition, as I said, S and T similarly, S on B and T on C. So now, instead of having a single query, we now have a summation of very many combinations of queries. So we have basically the combination where R is light, S is light, T is light, or R is heavy, T, S is light, T is light, and so on. So we have 2 per each factor, so we have 8 combinations in total. So potentially we might have to understand how each of the 8 behave. So let's look basically, because the query is symmetric, we look at updates just to R. Yeah. So we do delta R and assume we understand, delta R may be, would insert a heavy A or a light A. Okay. So we have now these 4 queries where Q, regardless whether, alpha was light or heavy, the other ones are light. So we are light on B and light on C. So this is basically the query we have. Yeah, the original query. This is in case, S is heavy, T is heavy. And in the case S is light is heavy and S is heavy, T is light. So we have 4 cases, yeah, which we have to update depending on the delta we get for R. So these are the deltas, yeah. So this delta R fixes A and B. So we have the C's in here, right, that remain, that we have to process. So let's go step by step. So let's look at the case where S is light and T is light. We are in this situation. We have the delta, which alpha and beta. We sum over C. And now we have the C's for the beta and the C's for the alpha. What can we use here? We use the following observation. Because S is light on B, on beta here, right? Then the number of C's we have here would be upper bounded by n to epsilon, yeah? But that's enough. We don't care about the C's here, because if we take an intersection of 2 lists, you can do it in time proportional to the minimum of size of the 2 lists, right? Because we can always iterate over this and do lookup in the other one, okay? So then the overall time here would be O of n to epsilon it takes to intersect the lists. And that would be the time to do this insert or delete, yeah? So imagine now we are in a situation where we are heavy and heavy with the same update there, yeah? So it will be an update that, says that alpha, no, so some update. And now we have S heavy and T heavy. So what do we know now? We know that T is heavy on C, yeah? So effectively, if we look at the C's that can be possibly paired with alpha, there can be at most n to 1 minus epsilon heavy values, right? There cannot be more than that because all C values in here are heavy, right? And each of them takes at least n to epsilon pairs. So we have to have at most n to 1 minus epsilon of them. So now we do the same trick. You know, we have a bound on the size of this list. You know, we just take that as the time it takes to intersect the lists. So then we get O of n to 1 minus epsilon overall time. Yeah, which is the size of the list of C's paired with the alphas. Good. So it looks quite nice, right? It's like a nice ride. But no, there will be some wrinkle. There will be some hiccup at some point. But before then, let's consider the case where we have S light and T heavy. So now, how many C's do we have here for the beta? We know beta is light. So can be at most n to epsilon. Now, T is heavy on C. How many possible C's we have paired with an alpha? Well, there can be at most n to 1 minus epsilon C's in that heavy part of T. So we have now bounds from both sides. This is n to epsilon, this is n to 1 minus epsilon at most. So basically in this case, we get the minimum of the two, yeah, which is n to minimum of epsilon and 1 minus epsilon. And now we say, okay, this is the last case. If we pass this, then we are done. We are happy. But look here. What happens here is this. Hold on. Happens that because beta is heavy here, we have nothing to say on the C. Right? We can say on the possible B values, but we fixed a particular B value, right? There may be that B value may be paired with as much as we know linearly many C's. On the other side here, we already know that C is light in T, but it doesn't say anything about how many C's are paired with the alpha. So we are now in a problem. You know? We don't know how to get around this. And the solution is we materialize. So whenever in doubt, we materialize, okay? So we materialize here. We aggregate away C of these two things, and we get this view. Now the price to play is that we have to maintain this view, but we will see the view can be maintained efficiently. But once we have this view, then doing the update to R is just a simple lookup, and that will cost us essentially constant time. Yeah. So this is basically what we got so far. We got n to epsilon, n to 1 minus epsilon, n to epsilon, you know, for these two approaches for the third case, and constant. So overall, we get this update time for these 4 cases. We also have these views to maintain. And, you know, I think in 6 minutes I'm done. Is that okay? Yeah? Is that okay? Or, yeah? Okay, good. So let's actually see this view, how we can maintain this view. So this view essentially says I'm heavy on S and light on T. So obviously, if I do an update to S, this gamma here is paired with at most n to epsilon A's. So that's fine. Yeah. So this is the time n to O of n to epsilon. If I do an update to T, and T is light, then I know at least that the number of B's here at most could be n to 1 minus epsilon. So that's the thing. I get this time. So I can, in both cases, go below linear, you know, depending on alpha. So that's the thing that, you know, the maintenance complexity then becomes this, and this is because it is the size of the actual extra views we actually have to put in there. Okay? Okay, so one thing, however, I would like to say is that, you see, we based everything on this heavy light partitioning. But what happens if after a number of updates, our assumptions, initial assumptions about what means heavy and light change? Or, you know, our threshold was also based on the size of the database, N, but N can change as well. So for this reason, we have actually to, every now and then, you know, redo the work, you know, so that we still maintain valid thresholds. So that is, first, updates can change the frequencies of values. Imagine A was light, but we do a lot of insertions, and now A gets more tuples, right? And passes the threshold. A becomes heavy. The tricky thing is this, that when we do this, we have to transfer about O of n to epsilon, because this is the threshold, right? From here to there. Yeah. And that costs non-trivial time. So the time complexity to do this would be that, because, you know, there are n to epsilon tuples to be inserted, and each of them costs this time, right? So that's actually could be above linear. Similarly, updates can change the heavy light threshold. You know, initially that was the threshold because that was the size, but now sizes increase. And now whatever was light before is not anymore light, let's say, or heavy. Yeah? So in this case, we have to recompute the partitions and the views from scratch. So it will be basically, it will take us time, and for all the records we have in the database, for each of them, we take this time to do the update. So, however, what is actually neat is the following, that when we have updates, right, we can actually only need to do the rebalancing, yeah, for the frequencies only after a certain number of updates, a minimum number of updates, like, you know, n to epsilon. And that if we do this, then this doesn't change the overall asymptotic time, yeah? But it means that we get an amortized update time now, instead of getting the time we see before. But to be honest, you know, as a small parenthesis, amortization, we need any way to deal with the hash function, with the hash maps, right? Because they also give you some constant update time, constant lookup and so on, only amortized. You know, on average, they don't give it to you provably all the time, yeah? Whereas for the other thing, when database changes, you can wait for n updates to happen. And then if you wait for n updates to happen, amortized over n updates, it remains also with the same nice complexity. So this amortization has to be done. There are ways to de-amortize, of course, the standard techniques, like while you actually, you know, you do the inserts and deletes, you give credits. You know, you keep some credits in mind, you know, for the things you have to do later every now and then, yeah? It's different from the kind of credits, governments do, because, this credit is that invest credits for the future. They have credits for what they did in the past they didn't pay. This is a totally different situation, but the concept is the same. It's called credits, yeah? So imagine that you could do it differently. You could, while you do the inserts and deletes, you can also construct in the background another database that assumes that you already have, you'd have to double the size of the database and so on. So that's also a way to cope with this, but of course, it's not a practical way. You know, it's better to be lazy here, right? Lazy is virtue. Okay, and that's basically what I wanted to tell you guys. There is much more if you want. You know, you can go about optimality and so on, but that's for later if you want to reach out to me. Thank you.
Folks, let's end down.
Thank you guys for being here, actually, you know, for all the wonderful questions. It was a pleasure to actually interact with you. So it reminded me of the time 10 years ago when I taught in the other room next to this one. Yes. Thank you.
Okay, next week on Tuesday, we talk about the AGM bound. A beautiful bound, theoretical, but I think it's very interesting.